Consider the next example. So using the properties of determinants, prove that 1a square, 1b square, 1cc square is equal to a minus b minus c minus a. So consider the LHS of the above determinant 1a square, 1b square and 1cc square. So we will apply the operation R1 implies R1 minus R3. So we have choose this operation to get the term A minus B on the RHS. And then to get B minus C, we will apply the operation R2 implies R2 minus R3. So we get 0 a minus c a square minus c square as the elements of R1, and R2 elements will be 0 b minus c b square minus c square. The elements of R3 will remain as it is. Next, using the identity a square minus b square, we can write a square minus c square as a plus c into a minus c, and b square minus c square as b plus c into b minus c. So we will be taking out a minus c common from R1 and b minus c common from R2 respectively. So the remaining determinant will be 0 1 a plus c, 0 1 b plus c and 1 c c square. Now we will expand it using C1 because C1 is consisting of maximum number of zeros. So A minus C, B minus C. So since the first two elements of C1 are 0, no need of expanding. So directly we will expand it using the last element, that is 1. So 1 into we get B plus C minus A minus C. On simplifying we get A minus B, B minus C and C minus A. So which is the required RHS. Next example, using the properties of determinant, prove that 1 1 1 ABC a cube b cube c cube is equal to a minus b, b minus c, c minus a into a plus b plus c. So again consider the LHS. So we can see all the elements of R1 are equal to 1. So we will start using column operations. So the first property will be C1 implies C1 minus C2. So we get A minus B. So C1 minus C2, 1 minus 1, first element minus first element, it will be 0. Next, second element minus second element, we get A minus B, and third element minus third element, we get A cube minus B cube. Next, we apply the property C2 implies C2 minus C3. So first element of C2 minus first element of C3 is 0. Second element, it will be B minus C, and third element minus third element, it will be B cube minus C cube. The elements of C3 will remain as it is, that is 1C C cube. Next, we make use of the identity x cube minus y cube, which is equal to x minus y into x square plus xy plus y square, and expand the elements in R3. So first row elements will be as it is, second row elements will be as it is, third row using the identity a cube minus b cube can be written as a minus b a square plus ab plus b square, and b cube minus c cube can be written as b minus c into b square plus bc plus b square. Next, we will take out a minus b common from C1 and b minus c common from C2. So the determinant will be of the form 0 1 a square plus ab plus b square, 0 1 b square plus bc plus b square. and 1c c cube. So we will expand it using R1 because R1 consists of maximum number of zeros. So on simplifying, we get 1 into b square plus bc plus c square minus a square plus ab plus b square. Next, on simplifying, we get a minus b minus c into b square plus bc plus c square minus a square minus ab minus b square. So b square and b square term will cancel off, and using the property a square minus b square, we can write c square minus a square as c plus a c minus a. So you can see that in the first two terms in the bracket, c minus a is common. So when we take out c minus a common, we get a minus b minus c minus a. In the first term, b will remain, and in the second term, c plus a will remain, which can be rearranged and written as a plus b plus c. So this is the required RHS. Next example, using the properties of determinants, prove that x square yz, y square zx, z square xy is equal to x minus y minus z, z minus x into xy plus yz plus zx. So again consider the LHS. So in the RHS, the first element what we require is x minus y, the second element is y minus z. So we apply the operations row wise. So when we apply the property R1 implies R1 minus R2, we get the first factor on the RHS, that is x minus 1. So R1 minus R2, the elements of R1 will change to x minus y, x square minus y square, and yz minus zx. So when we take out z common, we get y minus x as the third element. Next, apply the property on R2. So R2 is equal to R2 minus R3. We get y minus z, y square minus z square, and xy minus zx. When we take out x common, the remaining factor will be z minus y. Keep the elements of R3 as it is. So in the first row we can take out x minus y common, and in the second row we can take out y minus z common. So x minus y outside and y minus z we can take common. So the remaining determinant will be 1 x plus y minus z, 1 y plus z minus x, and z square xy. Now next we will apply the property R1 implies R1 minus R2. So we get 1 minus 1 is 0, x plus y minus y plus z, it will be x minus z, and the third element will be minus z plus x. Next, write down the elements of R2 and R3 as it is. So take out z minus x common from R1. We get x minus y, y minus z, z minus x. So 0 minus 1 minus 1, 1 y plus z minus x, z square, and xy. Next, apply the property C2 implies C2 minus C3. So the elements of C2 will change to 0, y plus z plus x, and z square minus xy. So we can see R1 consists of maximum number of zeros, so we will expand it using R1. We get x minus y, y minus z, z minus x into minus 1 into z square minus xy, and z into y plus z plus x. So on simplifying the bracket, we can see z square and z square will cancel off, and we can multiply all the terms by -1. So we get x minus y, y minus z, z minus x into xy plus yz plus zx, which is the required RHS. Next, using the properties of determinants, prove that x plus 4 2x 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 x plus 4 2x 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 x plus 4 is equal to 5x plus 4 into 4 minus x whole square. So solution, again we start by considering the RHS. So see, in this particular determinant, you can see all the diagonal elements are same as well as the non-diagonal elements are same. So in such case, we can either apply the row operations, that is R1 implies R1 plus R2 plus R3, or C1 implies C1 plus C2 plus C3. So we will consider the column operation. So elements of C1 will change to 5x plus 4, 5x plus 4 and 5x plus 4. So 5x plus 4 is common in C1. So we get 5x plus 4, 1, 1, 1, 2x, x plus 4, 2x, 2x, 2x and x plus 4. So apply the property R2 implies R2 minus R1. So we get 5x plus 4, 1, 2x, 2x, 0, minus x plus 4 and 0. Next, on applying the property R3 implies R3 minus R1, we get 1 minus 1 as 0. Next, 2x minus 2x is 0, and x plus 4 minus 2x will be minus x plus 4. Now we will expand the determinant using C1. So 5x plus 4 into 1 into x minus x plus 4 and minus x plus 4 is repeated 2 times. So it will be 4 minus x into 4 minus x, which is equal to 5x plus 4 into 4 minus x whole square, which is the required RHS. Next example, using the properties, prove that y plus k y y y y plus k y and y plus k is equal to k square into 3y plus k. So solution, consider the LHS. So again we can see the diagonal elements are same as well as the non-diagonal elements are same. So either you can apply row operations or column operations. So we will apply the operation C1 implies C1 plus C2 plus C3. So we get 3y plus k, 3y plus k and 3y plus k as the elements of first column. Next, take out 3y plus k common. So we get 1, 1, 1, y plus k, y and y plus k. Next, similarly apply the properties on rows. Try to fix the first row as it is and convert the elements of R2 and R3 into 0. So we'll apply the property R2 implies R2 minus R1. So first row elements will remain as it is. Second row element will change to 0, k and 0. Similarly apply the property on the third row. So R3 implies R3 minus R1. Again we get 0, 0 and k. So expanding using C1, we get 3y plus k, 1 into k. So we get k square into 3y plus k, which is the required RHS.